Molecules are nature's building blocks, but there are natural limitations to what we can do with them, given the confines of classical chemistry, where we can only play with what Mother Nature has given us. But molecular scale manufacturing can now give us the tools to accomplish our wildest dreams. Immortality, supercomputers, and an endless supply of clean water. And yes, discovering a single molecule can make a world of difference. In fact, historical periods have often been characterized by the materials that they were able to harness during that time. We have the Stone Age, the Bronze Age, and the Iron Age. A civilization is only as good as what it's built from. And today, we live in what you could call the Silicon Age, the Oil Age, and quite possibly, the Graphene Age. The term Graphene Age is not an exaggeration, because it's a material that could be so influential to society, future historians will use it to define the age in which we live.
What's going on here? Why is everything...
Graphene.
Everything is
Graphene.
in the future.
Oh my... Impossible! He's lying!
Sci-fi author Neil Stephenson even coined the term Diamond Age to describe a future society where we'll be able to make everything from a single compound called diamandoid, manufactured by nanoscale machines. A so-called Diamond Age might be very far off, but a Graphene Age might just be feasible. Graphene is to our world what Mithril is to Middle-earth. Not only is it a durable material, but it also has quite a number of additional uses that would take you forever to list. Graphene could potentially replace silicon as the go-to material for our transistors and circuits. It could charge our electric cars in minutes, make unbreakable smartphone screens, build space elevators, create the base for new supercomputers, enable efficient solar cells, filter the salt from our seawater, clean up nuclear waste, and most importantly, biocompatible properties for technology that could extend our lifespans. Graphene elastomers are the FDA-approved, quote, safe material that we've always been searching for, making up the foundations of neural electrodes used in BCIs, coatings used for prosthetics, and brain-computer interfaces that could rescue us from the shackles of aging. For those who haven't heard of it yet, graphene is an allotrope of carbon first discovered about a decade ago. It can even be found scattered in the graphite of your pencil. But recently, we realized that it was kind of a wonder material with countless uses. Graphene itself is just a transparent 2D sheet of carbon only a single atom wide, and yet, it's one of the strongest materials known to humanity. You could stretch graphene by a quarter of its length, and because of its ultra-strong interatomic bonds, it'll still remain stiffer than diamond. In fact, you could take an elephant, balance it on a sharpened pencil, and then place that pencil on a sheet of graphene as thick as saran wrap. And, believe it or not, that sheet will not break. Today, we can even create graphene aerogels that are just 99.8% air, yet stronger than steel, as well as carbon nanotubes, where graphene is rolled up into layered cylinders, or fullerenes, which can be mixed in to strengthen other materials. Graphene is such a versatile material that you could put it into many different composites, making up things like body armor, skeletal enhancements, or bionic augmentations. It's not only strong, but it's also extremely light, which means we can make airplanes dramatically bigger, or just keep them regular sized, with dramatically reduced fuel cost. Graphene is also one of the most flexible materials known to humanity, which means we can make smart clothes, and even foldable desktop monitors that you could carry in your pocket. But it's not just the tensile strength and flexibility that make it useful. In fact, graphene's potential superconductivity could also make the world brighter. A Canadian-based company called Graphene Lighting developed a light bulb containing filament-shaped LED-coated graphene that could conduct heat and electricity more efficiently than a traditional LED light bulb. This is because carbon atoms in graphene are densely packed into a two-dimensional hexagonal pattern we call a benzene ring, which creates ultra-stable bonds and free electrons, an unobstructed particle flow that gives graphene its conductive characteristics. And as we mentioned earlier, Graphene also has high biocompatibility, which means it could be used in biomedical applications like implants, brain-computer interfaces, and cell grafts that could extend our lifespans. For example, if you have a damaged eye, the biocompatibility of graphene transistors could let us create a mesh that interacts with your optic nerve, helping to send image data to your occipital lobe and visual cortex. The list goes on, from medical scanners to bulletproof vests, spacecraft, batteries, quantum computers, and even DNA sequencers. A material that will revolutionize every industry in the modern age. So, if graphene is so great, then why aren't we funding it? And why isn't it everywhere? Well, mainly because graphene is hard to isolate, and its synthesis is very difficult because it consumes valuable resources, making it one of the most expensive materials to manufacture. So with that said, why should we believe all this hype about graphene? Will it ever be practical, and could we ever enter a graphene age? Well, I wouldn't give up hope just yet, because we've only just recently discovered it. It's been hidden in plain sight longer than you can imagine. In fact, all you need is a pencil and some scotch tape, and you can even manufacture tiny flakes of graphene yourself. After all, the graphite of your pencil is really just tiny flakes of graphene piled up. So we know graphene can take many different shapes. It's just a matter of how we synthesize it on an industrial scale. This is a material that physicists originally thought would be impossible to make, since thermodynamic fluctuations would curl it up. However, two scientists at Manchester University figured out that this wasn't the case. A team led by Dr. Andrei Geim and Dr. Konstantin Novoselov were the first to isolate one-atom-thick flakes of graphene using a repetitive shaving process centered on tape. Even though the amounts they got were very, very small, it still won them the Nobel Prize in 2010. The process was incredibly expensive, but fortunately, graphene production has gotten somewhat cheaper since then. The key to a graphene age is overcoming problems of synthesis. The modern techniques we use to exfoliate graphene rely heavily on aggressive oxidation, high-energy mixing, or sonication, none of which are very efficient. Currently, there are 3 conventional ways we can make it. First, mechanical exfoliation, a labor-intensive process where we press graphene into one-atom-thick sheets, thinning graphite with a smooth silicon substrate and peeling it off layer by layer, which, you guessed it, sounds very inefficient and uneconomical. Second, there's chemical reduction, which produces substandard quality of graphene. Not to mention it produces toxic chemical byproducts that would wreak havoc on the environment. Third, there's chemical vapor deposition, where we heat a copper substrate in a furnace at 1000 degrees Celsius, annealing and tempering the substrate while introducing methane and hydrogen gas so that the carbon atoms get captured. It forms a continuous one-atom thick sheet, but this process isn't ideal either. Recently, scientists have discovered a 4th way to manufacture graphene, and it's cheaper than the previous 3 methods. A team of physicists from Kansas State University, led by Dr. Chris Sorensen, have patented a new process to produce graphene by the gram extremely efficiently, using only hydrocarbon gas, oxygen, and a spark plug. It's made by putting acetylene or ethylene gas in a chamber, introducing oxygen to that chamber, and timing a contained detonation in which the spark plug will create flakes of graphene in bulk. More interestingly, this groundbreaking process was discovered by accident as a byproduct when the team was working with carbon suit aerosol gels. Dr. Sorensen's method is interesting, but it doesn't produce pure graphene. It only creates an oxidized version of the material, which doesn't perform as well in intended applications. To solve this problem, another team at the University of Connecticut, led by chemistry professor Doug Adamson, has figured out how to even more efficiently synthesize graphene in its pure unoxidized form. Their method, published in the journal ACS Nano, described a process where we place graphene in an interface of oil and water, cover the interface, and then trap overlapping graphene sheets while locking them in place with plastics and cross-linked polymers. In fact, another study, published in the journal Nature Communications, describes an even simpler process where we heat soybean oil to 800 degrees Celsius on a nickel foil, causing carbon atoms to arrange into a one-atom thick sheet, and cutting the production costs of chemical vapor deposition almost tenfold. But this process still has a ways to go. The largest graphene sheet we've created thus far was only the size of a credit card. If all else fails, there's always PECVD, or plasma-assisted chemical vapor deposition, a new cutting-edge method for graphene synthesis, where we take a piece of copper, introduce it to hydrogen plasma and cyanide radicals, clean off the copper oxide, pump in methane gas, separate the hydrogen, and then have the copper take up the carbon atoms from the methane, nucleating them into graphene. In general, it seems that every few months, a new method for synthesizing graphene is developed, dropping the manufacturing price $1 at a time. Back in 2008, graphene was one of the most expensive materials on Earth. But now, companies have started selling it in increasingly cheaper and larger quantities. Graphene production overall has grown from 12 tons in 2009 to over 390 tons last year, and climbing. Seeing some hope of graphene's industrial practicality, scientists are now taking the first step to actually delivering on all the hype surrounding graphene's endless applications, including but not limited to graphene clothing, thanks to its hydrophobic properties, limitless clean energy, thanks to its vibratory properties, superconductors, thanks to its valence of 4 and sp2 hybridization, and lastly, limitless clean water, thanks to its porous honeycomb structure. Firstly, we have graphene-based clothing, which, while still being very expensive, does exist commercially. Some graphene-based clothing lines are already available on the market. In fact, apparel startup company Volleybak just released the world's first $695 futuristic graphene jacket, with a high-stretch nylon coating on one side and a layer of graphene on the other. This makes the jacket waterproof, snow-resistant, and yet breathable like cotton. When the reversible jacket is worn with the graphene facing inward, it evenly redistributes heat from your body, keeping you warm during the winter while resisting humidity and stickiness in the summer. The jacket won't stink or smell because the bacteria on your skin can't grow on graphene. Likewise, since water runs impermeably off the jacket, sweat can still evaporate out of it. The nylon keeps the water off the jacket, yet the graphene lets water run through it. Additionally, graphene-based clothing can be pretty tough. Silk spun by graphene-fed spiders is now officially one of the strongest fabrics on Earth. A new study published in the journal 2D Materials showed how adding graphene and carbon nanotubes to a spider's drinking water can make it 5 times stronger than conventional silk. This means that body armor made from graphene silk would be on par with the likes of pure carbon fiber and Kevlar vests. Another emerging application of graphene could very well be in clean, limitless, renewable energy. Scientists from the University of Arkansas studied the movement of graphene under a scanning tunneling microscope, not only finding Brownian motion, but also larger movements of the molecules within the graphene sheet itself. While this motion is very tiny, it could potentially be a source of harvestable energy. And with a graphene sheet 10 microns across, the researchers were able to generate 10 microwatts of power continuously without loss. This essentially means that one day, we could replace the concept of batteries by creating something called a vibration energy harvester, where a negatively charged layer of graphene between 2 electrodes could produce an alternating current. Imagine all the things we could do if we never had to replace a battery again. Electric cars could be useful for more than 5 years. Smartphones would be more convenient, and handheld gadgets would work almost like magic, letting us send, receive, and store information powered solely by the heat of room temperature. Granted that it can be produced efficiently enough, graphene would also technically be an endless resource. With carbon being the 4th most abundant material of space, it's not like we'll be running low on it anytime soon. Not only is graphene a strong, wearable, energy-generating material, it can also be made into a superconductor, conducting electricity 140 times faster than silicon, and conducting heat 10 times better than copper. How can this be? Well, while regular graphite comes in flakes that give its electrons lots of directions they can go in, flat organized sheets of graphene can create an even larger surface where the electrons can skate around. This is because the carbon atoms of graphene have a valence of 4, allowing them to self-organize into a flat plane we call sp2 hybridization. It seems simple enough, but here's the big kicker. The non-bonded 4th electron of each carbon atom can actually be pooled together on the surface, in a kind of superhighway, speeding around the sheet at the speed of light and giving the carbon atoms superconductive capacities. Thanks to these miraculous properties, we could potentially have an electric car polymer battery that travels 500 miles in one charge, or even ultra-fast photonic chips that run on light rather than electricity, an idea we call optical computing. These properties would help us create a wireless world where no computers have cables, and Wi-Fi upload speeds are ridiculously fast. Additionally, scientists at Florida International University found that graphene could even become naturally magnetic at the atomic level. By manipulating the spinning electrons of carbon atoms, the team was able to turn the graphene into a one-atom thick magnet with potential applications in data storage. But that's not all. Because of graphene's 97% transparency to visible light, another use is in touchscreens. Electrical conductivity is necessary so the device can actually sense your fingertip, and it has to be transparent so you can see what you're doing. Graphene does both of these things astronomically well, and the material we use right now, indium tin oxide, is a good conductor, but it's expensive and brittle. Overall, you can see how a material that carries heat and charge seamlessly could be very handy. Because even with good conductors like copper, much of the electricity is lost to resistance, where it's converted into heat. However, graphene, a semiconductor in its natural state, can also become what's called a superconductor. By definition, superconductors don't generate heat, meaning they'd conduct flawlessly and have a zero-loss carrying capacity when delivering electricity. Scientists were able to achieve superconductive abilities in graphene by doping the material with calcium atoms. These graphene supercapacitors, produced by Skeleton Technologies, are now available for industrial power applications. But it doesn't stop there. Microprocessors built with superconductive graphene wires could potentially replace silicon and extend the life of Moore's Law, since we can only make silicon chips so small until they melt. Unlike a silicon chip, a graphene chip would not melt at the nanoscopic scale, and while we don't have graphene computing just yet, some graphene-based conductors are already being applied in a research setting. Recently, scientists at the Samsung Corporation, in collaboration with Seoul National University, found a way to synthesize graphene into beads with silicon dioxide, allowing them to increase their battery capacity by 45% and their charging speeds by 500%. Comparatively, Samsung's graphene batteries would only have about 12 minutes of charge time in comparison to an hour-long charge time for conventional lithium-ion batteries. If that's not amazing enough already, an even more groundbreaking study describes a method for making a graphene superconductor at room temperature. If we could make graphene into a superconductor in its natural state, it could potentially pave the way for, you guessed it, quantum computers. In the study, scientists used two graphene layers on top of one another, twisted at the perfect angle for conducting electrons with zero resistance. We already have quantum computing, but the superconductors we use for them only work at temperatures close to absolute zero, and the warmest superconductor temperature we have so far is only around -140 degrees. So, if we could make a room temperature superconductor, then could we ever have quantum computers? It probably won't be anytime soon, but that doesn't mean we can't develop other kinds of graphene-based computing. In fact, just last year, one of the first integrated graphene electronics chips has been produced commercially and marketed to pharmaceutical researchers by Nanomedical Diagnostics, a company based in San Diego. Scientists are very excited by the possibility of using graphene to replace silicon, not just because the electrons move faster, but also because they're subjected to less noise, as the molecular structure allows them to move from one side of the sheet to the other without having to detour around atomic potholes. But don't get too excited. All this is still at the research stage. It'll be at least another decade before we see graphene transistors rolled out into widely used electronics. Last but definitely not least, there's graphene filtration. Not only can graphene help us build fast-charging batteries, computer clothing, and superconducting transistors, it can also help to extend our life expectancy. One of the biggest problems in the future will be getting clean water to the 12 billion people projected to live on this planet by the end of the century. By the year 2050, water consumption will have grown by 40%, and a significant portion of the world's population will not have access to it. Over half of these people will be in Africa, where water is still the most difficult to get. According to the World Health Organization, horrifying statistics show that at least 2 billion people around the world are also using drinking water contaminated with feces, transmitting diarrheal diseases like cholera, dysentery, typhoid, and polio. A simple filtration device would do wonders for life extension, since over 500,000 people die every year just from drinking contaminated water. While the Earth's surface may already be 71% water, 97% of it comes from the planet's oceans. So if we want more water, we'll need to pull the salt out of it in order to make it drinkable. So far, the only solution we have is an industrial-scale process called reverse osmosis, where pressure is applied to salt water to push H2O into low salinity zones. Through reverse osmosis, the country of Israel is able to get 1/4 of its fresh water from the Mediterranean Sea, but it doesn't come cheaply, costing about $3,000 US per acre-foot of water. However, it's only this expensive because pumping water through plastic membranes uses a lot of our energy. But if we could replace these plastic membranes with graphene sheets, then we could potentially reduce the energy needed for reverse osmosis, and thus filter salt water more cheaply. Using computer models, researchers at MIT believe we can now build a filter using hydroxy-decorated nanometer-scale graphene pores just wide enough to allow H2O molecules from seawater to pass through. The honeycomb-like structure of graphene creates a kind of net that only allows small molecules, as well as electrons, protons, and various ions to travel through, while blocking larger molecules. More research published in the journal Nanotechnology shows a prototype for a graphene oxide-based sieve membrane that can filter out the giant salt molecules. This solution means that we might not only be looking at industrial water filter plants, but potentially tiny filtration systems in every home. Every family could have water free of Illuminati mind control drugs, or whatever else you believe to be lurking in your tap water.
We're breaking the conditioning! Ah!
This goes especially for the city of Flint, Michigan, which has a well-known contamination problem with lead in their drinking water. Graphene filters won't only filter water though. In fact, they would allow for the storage, separation, and purification of any small gas, liquid, or pharmaceutical you can think of. A good nanofilter system holds the promise of creating carbon capture plants that can deconstruct CO2 from the atmosphere, catch radioactive waste particles, and even extract the 20 million tons of gold particles floating around our oceans. A graphene filter plant that catches gold could help pay off the United States' $20 trillion debt. Also, consider energy. There's more lithium and uranium dissolved in our ocean water than is thought to be presently available on land, meaning an endless supply of nuclear power plant fuel and electric car batteries is hidden in our coastlines. Most importantly, graphene filters might also help us extract industrial quantities of xenon to accelerate laser technology and deep space exploration. The dense noble gas we call xenon is the preferred propellant for NASA ion drives, since its inert atomic properties make it less corrosive to ion engines than cesium fuel. The only problem is that we have so little xenon in reserve that if NASA were to use it for just one space mission, they'd be using up about 10% of the global annual production rate for xenon. Fortunately for us, though, xenon is naturally occurring in the Earth's atmosphere, and if we could design nanostructures small enough, we could passively harvest trace amounts of its gigantic atoms. Instead of needing to compress xenon, which is energetically expensive, we might be able to design walls or surfaces where the atoms can stick to. If we were able to tailor the size of the pores within the lattice, we might be able to construct a very selective filter to extract anything we want. The nanotechnology startup, NUMAT, founded by Dr. Ben Hernandez and Dr. Omar Farha, is already trying to do something like this, where they plan to combine graphene filters and MOF filters to catch xenon gas. MOFs, or metal organic frameworks, are essentially Brita filters on steroids. Open cage structures similar to graphene in the sense that they can filter selective kinds of molecules. But again, don't get too excited, because creating these filters won't be simple. The map is not the territory. What happens on small-scale micropatches of graphene in the lab, and a football field-sized sheet of graphene in an industrial filter plant, is a world of difference. In conclusion, graphene technology will drive innovation in almost every industry to inconceivable heights. We might truly see the graphene age within our lifetimes. It's just a matter of how fast we can accelerate the industrial scale-up. While graphene extraction may seem impractical because of purity issues, don't forget that we had the exact same problems in the silicon industry a century ago. And yet now, silicon is in all our electronics. With the potential to create anything from bionics to advanced supercomputers, graphene is truly the material of tomorrow. Turns out that the key to a future without aging, pollution, and drought isn't impossible after all. It was inside your pencil all along.